Okay, let's look at Faraday's and Lenz's law. Okay, so let's say we have a coil or a loop of wire or a coil of wire here, and we have a magnetic field that's set up by something somehow to go into the page, right? See, these X's mean the field is into the page, so the field is going straight down in. And so the wire, we're going to think of this as a loop of wire that's moving in this direction, all right? And we're going to trace what happens to the wire, what kind of fields are induced, what kind of currents are induced, right? Remember, voltages are induced. Faraday says that the induced voltage is the number of turns times the change in flux over the change in time, right? So we have to have the flux or the field that it feels changing in time. Flux in general is B times A, so just kind of think of it as either A changing or the angle changing or B changing as we go in. So we're going to assume it's the same angle, and so the changing flux, remember flux is BA cosine theta, right? So A is going to stay the same, theta is going to stay the same. The only thing that's going to change is how much B is cutting through the loop. So out here, there's no field. Field's all over here. So there's not any field, and so there's no change in field. It's not coming into the field. There's no change in field. So B equals 0. Let's start with induced voltage, E equals 0. And so then I equals 0, and so then the induced field equals 0. All right, so let's call this the external field. All right, this is caused by some external source, not from the wire itself. All right, and we're wanting to know the induced field that the wire is actually making because of the current that comes from the changing flux. All right, so flux has to change, and then we get an induced voltage. It's a closed loop, so we're getting induced current, and that current makes the field of its own, right? And Lenz says that current is going to be in a direction that this field would oppose the change that's happening, right? Because the loop doesn't like changes, right? It wants things to stay the same. All right, so at this position, we're moving the loop into the field, right? And the area should be the same. Although it looks bigger, it should be the same, right? So it's moving in, so the field is growing, it's getting stronger, it's feeling more field going down, right? The loop is feeling more field going down, right? The field is growing or gaining strength in the down direction here. And so what is the loop going to do? It liked having no field, right? So it's going to say, no, go the opposite way. So it's going to try to make a field going up, right? So, and we're always considering the inside of the loop is where the action happens. It's the enclosed field inside the loop. And so the field from the loop, the B induced, or just B, let me just call it B, is going to be up because it's growing field down. It doesn't like down. It wants it to be 0, so it'll say no, field is up. So it's going to oppose the change that's happening, right? So what kind of current direction do we get then to have a field up on the inside, right? So the field is the fingers, and so the current has to be going counterclockwise, right? So I, and it's the same I everywhere in the loop. It's a closed loop, right? So the current is going that way, and so it's making a field up on the inside and of course down on the outside. For the B, I should have made it with blue, but mostly we're worrying about what's happening on the inside, right? So it's coming into the field, it's feeling the field. The external field says down, down, down. The internal field is down. It doesn't like the change, so it's going to push back. It's going to push up to keep it from, to try to keep the equilibrium, or try to keep it how it was, right? As a result, current is going to go counterclockwise. Okay, so now let's say we got over here to this position. The loop is moving, it's stabilized. Anyway, kind of slowly moving, but now it's still moving here, going this direction. but it's in a nice constant field. This is a constant field, and the currents have died down, and now that it's in a constant field, as it's moving, A is not changing, B is not changing, angle's not changing. So while the whole loop is inside, right here it was coming into the field, but now it's all inside the field, right? And so now, again, the induced is going to be 0 because there's no change in field. And so then the current is equal to 0, the B induced is equal to 0. Everything is 0 again. No current, no reaction from the coil. All right, but now, keep on moving. You got velocity over here. Now it's coming out. So let's say the field ends something like this, right? So it was happy in the field with the field going down in the loop, right? The loop was happy. But now as we're coming out, it's losing the down field. So the field strength in the negative direction is getting weaker, right? The field isn't really turning up, but it's getting weaker in the down direction, right? So what is the loop going to do? What's the induced current going to do? It's going to try to make the field stay down, right? It says I liked it down, I got used to it down, so I want it to go down, right? So it's going to make a B induced down to try to keep the status quo, try to keep it how it was, right? So how do we get B, an induced B that goes down? What kind of current has to be in the loop to make that happen? Field down in the middle, so the current is going clockwise now. And again, it's the same current everywhere in the loop. It's all going clockwise to try to keep what it had, try to keep that down field that it had, but it's losing because it's coming out of the field. All right, and then finally we're over here again, outside the field, no field at all, anywhere, and so there's no changing field, no changing flux, no change at all. So then the induced voltage is 0, the induced EMF or voltage is 0, current is 0, B induced is 0, everything's back to 0. All right. So the interesting parts are where it's changing, where it's feeling a change, and it tries to basically fight back and it causes a current that tries to equalize the field and keep it like it was. Okay. Forces on the coil. What was I thinking there when I wrote that? Let's ignore that one. Let's look at, I think I was thinking about sorry. Let's go back. I see what I'm doing now. We're going to this picture down here. So this is another coil with some loops, and think of it as if my calculator was a loop, it's down in there, and so it's a coil of wire, say, wrapped around the edges of my calculator, sitting in the field at an angle like that. Maybe I don't know if I have something smaller. So where we can see these Post-it notes. So the coil is in the field at an angle. The field is going down into the page still. All right. So, and the coil is wires wrapped around like that. Right, a coil of wire in there. So what kind of forces then would this, if we have, we'll have to assume we have some sort of current. Let's just assume we have some current, and we just want to know what are the force directions because we don't have any information. All right, so if we have a current, let's say the current is coming out of the page here, going down, and then going into the page there, and it'll be coming up on the other side. So the current would be going going around like this, right, in the plane of the paper kind of thing. Okay, so these are the eyes. All right, so what direction is the force? Let's do this one that's going into the page. We've got I cross B I cross B. I and B are in the same direction. What happens when we do that? So this side is going to have 0 force, right? Because I and B are in the same direction. Similar kind of thing happens here. I is coming out of the page, B is going into the page, but they are in the same direction, right? Same direction, or same path, same line of action. One's opposite the other. So the force on this long side going into the page is also equal to 0. How about the force on this side here? All right, so now we've got I cross B. Ooh. I cross B, so the force on this side would be in this direction. And then if we do on the back side, the force is going up, or going, like this, right? So we've got I cross B, so the force would be in this direction on the down inside of the coil, right? So the force is, this one's pushing this way, this one's pushing this way, so it would tend to rotate the coil like this, right? Try to make it turn in here until it got this way, so all the forces would be balanced. Okay, so that is the idea there. Let's see. It should have been a little bit more clear which one we're talking about. So here, I think this one was gonna apply to the figure down here. And so we want to know, what is the induced voltage? We sometimes call them give the induced voltages a script E called EMF, but anyway, it's a voltage that's induced. What is the induced voltage if, so we have L is 5 centimeters, they're moving at 3 meters per second, and we have this B field, now we're going to say it's 0.3 Teslas, which is a pretty big field, but we'll just go with it for some numbers. Okay, so what do we have happening here? Well, we have a changing, so this loop, we're going to have a loop through the meter here. We're going to have a loop that is, maybe we want to measure the current instead, so we have a kind of a small resistance. And so this loop is going to feel a changing field, or changing flux, because it's getting more area, right? The area is the cross-section area of the loop. B is constant, it's staying the same, but A is getting bigger, and theta is constant, it's not changing, or it's not twisting in here. And so we're going to be getting a bigger A, right? We have a formula for this kind of situation, but we can just go ahead and use, so that the induced voltage is B times L times velocity, all right? And so velocity is the change in width versus change in time, and so that's the changing area comes in from the changing velocity. So we can use E equals BLV, and there may be a negative sign in there, just to go along with Lenz's law to tell us the direction. Let me see if your equation sheet has a negative sign on it. Okay, I can't even find the equation on it. All right, so you probably want to go ahead and add that equation to your equation sheet. What happened to that? I lost that on all the equation sheets. Okay, let me just double check that equation, but well, let's just go with positive. All right, and again, it's induced. We can figure out the current direction as we did up here with Lenz's law to decide the how it would. We'll do that here in a minute to find the direction. But induced voltage, we'll just go with magnitude-wise anyway. It's BLV, and so in this case, B is 0.3 Teslas. The length of this bar. So I guess I should explain what's happening here. So we have conducting rails and we have a conducting bar that's making this loop, right? And then as we move this bar, basically the loop is getting bigger, right? And there's more field inside the loop then because the whole thing is submerged in this magnetic field. And so it will get an induced voltage, right? Which is BLV. L in this case, did I give an L? 5 centimeters. And V, I said, was 3 meters per second, just to have some numbers. All right, so the induced voltage is, let me see if I can see the calculator here. Induced voltage is 0.3 times 0.05 times 3. 45 millivolts. All right, not a huge induced voltage, but it's something. So if this is a shorted out loop, well, let's just go with that for a minute. Let's go ahead and do some directions. I want to get some idea of what's going on here. So what direction will the current be going in this loop? All right, so what's happening? This loop is here. As this goes out, it's seeing a stronger field going down, right? Loops don't like change, so what's it going to do? It's going to make a field going up, right, on the inside. We're always talking about on the inside. So it's going to make a field coming up on the inside. It'll go out, down on the outside, but that part doesn't matter. And so the induced current then is to cause a field that's going like this, right, up on the inside, down on the outside. So the induced current must be going around like this. So I induced. Okay, I is going around like this. All right, and so if there's some resistance, maybe there's some resistance here, and there's some resistance in the wires, but we'll just kind of think of it as all being lumped in one spot. Then the induced voltage is across this resistance, and we could get the induced current then, so it's really the voltage that's induced, but if we have a closed loop, they'll have some resistance, and we get the voltage, and so we can calculate the current from voltage over current. V equals IR, so remember a good old Ohm's law of Burr. E is the voltage, so I is V over R, so we have the 45 millivolts. And did I give a number for R? Let's say R was 2 ohms. And so we get, what, 22.5 milliamps of current. Okay. Again, totally made up numbers, and I'm doing things out of order. But anyway. Okay. Now on part D, it says, okay, how could we get 1 volt, right? 45 millivolts is pretty small. How could we get 1 volt induced? So we want E to be 1 volt. So then BLV, what can we change? Let's say we can change the speed. We can move it faster, right? And so let's solve for V, trying to make a script V for velocity, just keep track of it not being volts. But V is E over BL, so that is 1 volt divided by B, we said was 0.3 Teslas, and we said L was 5 centimeters. So to get 1 volt, we would have to do 1 divided by, and let's put this in parentheses on the bottom, 0.3 times 0.05. 66.7 meters per second. That seems pretty fast. But we have to have a velocity of 66.7 meters per second. Move that guy fast to get an induced voltage of 1 volt. Right? And so it would be positive. If our velocity was out, it would be something like this. And then it says, what if we wanted to get negative 1 volts? What would we do if we wanted negative 1 volts? Well, to get negative out of this, we would just bring the bar in, or just do the opposite direction. So we would have to go, say the -1 volt, we would have velocity is negative 66.7 meters per second, basically pushing it in, making it smaller, making the field, so if it was making it smaller, then this would say, oh, I'm losing down, so I want to go down, so then the induced would be down, and the current would go the other way, so then the voltage would go the other way. Okay. What if we wanted our voltage to be a sine wave? We would go forward and backwards, right? Up, down. A sine wave goes up and then down, so we just go this way, this way, this way, this way in a nice smooth pattern, up and down, and we could get a sine wave voltage out. That's not how we usually make sine waves for voltage sources, but it's, possible. Okay. And then finally for G, I think we're talking about this picture here. So this idea now is, now we don't have an external field. They call these things rail guns and so forth. And so we can actually, if we have a source, say, did I have some numbers? I just said direction. So if we have some sort of voltage source, say the 12-volt voltage source, some sort of voltage source, probably tends to need a lot of voltage to get things to happen that need to, but again, positive is the long side, so we get a current flowing, right? Current flows around the loop. And so now if there's a current flowing, then the current itself is going to make a field. So this was an external field caused by magnets or something else, but here now we're just going to have the current making a field. So get your thumb going in the current direction. The field is going around here, it's coming out on this side, yeah, going down in the middle. Here it's going down in the middle and out on this side, right? That, and then this way, again, down in the middle, out on the outside. Something along those lines, all right? And so, in this case, the bar is free to move, and we'll say it's easy to move, and so there will be a force on this guy that in a railgun it would be probably like a plate or something behind a projectile, something that's going to get shot out of the thing, shoot a potato or something, I don't know. And so what would be the force on this rail, or what direction would be the force on this rail, hopefully going that way to shoot the thing out. I don't know if I drew it right or not, let's see. And so the B field, the B field from these wires is here, so this is B, right? And so it's not uniform, but there's field there. So we're going to do I cross B, B, so the force is out. So I got lucky, I guess. The force goes this way. All right, so if it was a big jolt of current, you get a big jolt of force and push the thing out and shoot the potato out, or the marshmallow, or whatever we have in there. Okay? And so all with magnetic fields caused from the wires or from the rails, whatever it is here, that is conducting the electricity, causing the fields, and then the current feels those same fields that it is generating, or maybe mostly from these side rails. The vertical thing feels the field from the side rails and gets pushed out. What if I had the force the wrong way, or what if we wanted to pull back in? What would we have to do? Turn the current around, right? If we turn the current around, then the B field turns around, and so then we would do, well, will that work actually? I cross B. I is now this way, B is now down. Yeah, so then the force is in. Yes, all that, everything gets backwards then. Okay, so it's a little harder to calculate the B field or calculate the force because the B field isn't uniform, and so we won't go ahead and won't calculate the numbers there, but we've got the directions anyway. All right, let's go ahead and stop there.